In our last video, we discussed how the kernel and the image of a linear transformation give us really important information about the algebraic properties of that transformation as a function from domain to codomain. If you haven't already, take a moment to go back and watch this video before continuing. We're going to use those ideas to classify linear transformations as to whether they are injective and or surjective. Here's how it works and why those two concepts are important and useful. Take the linear transformation from our previous video given by this formula and this standard matrix. Say I pick two different inputs to my function from my domain. Let's say the vector 3, 3, 0 and the vector 1, 2, 1. If I process these two vectors through my transformation, what I find out is that both of these two vectors have the same image in the codomain. You can check that t of 3, 3, 0 is the vector 3, 0, 3, but so is t of 1, 2, 1. So while these two vectors were different in the domain, this linear transformation is erasing those differences by the time we arrive in the codomain. And that's something that very often we don't want to happen. We generally don't like it when two different inputs from the domain of a function end up having the same output in the codomain. So when that happens, we say specifically that that function is not a one-to-one function. That's the language that we might have used when we were studying sets and functions in a previous course. When we apply that language to linear transformations, we just doll it up with a slightly different word, the word injective. So we say that a linear transformation is not injective if it's possible for two different inputs from its domain to have the same output in the codomain. Linear transformations that are not injective are erasing some of the important differences between distinct elements of the domain by the time their images arrive in the codomain. So to flip that definition on its head, we say that a linear transformation is injective when it's always the case that different inputs in the domain have different outputs in the codomain. An injective linear transformation is one that preserves and honors all the differences between different vectors in the domain by the time their images arrive in the codomain. Another way to say that a linear transformation is injective is to say that if v1 and v2 are different, any two different elements of my domain, then it must be true for an injective linear transformation that their images, t of v1 and t of v2, must also be different. If the inputs are different, the outputs must be different if our linear transformation is injective. But this is a difficult framing to work with because of the unequal to signs. So we often like to turn it around using the contrapositive of this statement, reversing the order of implication and also negating each of the propositions. And that looks like this. If the image of v1 and v2 is the same, then that must have meant that the original vectors in the domain were the same. We can't have two vectors having the same image unless those two vectors were the same vector to begin with. That is an equivalent framing, but it's one that's a little bit easier to work with because having these equal signs here give us criteria that we can work with in a proof, for example. So a one-to-one function, a one-to-one linear transformation, an injective linear transformation, is one where different inputs always have different outputs. So it's worth us looking at this example where injectivity failed. This was a non-injective linear transformation, and asking, what was it about this transformation that made this possible? Well, to answer that question, let's look at the relationship between these two different vectors. They're different in the domain, but they're different in a very specific way. In particular, we find out that the second vector v2 is actually the same as the vector v1 added to the vector -2, -1, 1. So whatever difference exists between v1 and v2, that difference is a vector -2, -1, 1 that we met in our previous video. Indeed, -2, -1, 1 in our previous video was a basis for, in particular, an element of the kernel of our linear transformation. And remember, the kernel is the set of everything that a linear transformation collapses to zero when it does its work. It's everything that maps to the zero vector in the codomain. So -2, -1, 1 is what we call a null vector for this linear transformation, because this linear transformation squashes that vector away to zero when it does its work. So the difference between our two vectors v1 and v2 is a vector -2, -1, 1 that we know this linear transformation sends to zero. It's a vector that lies in the kernel of t. And so when I apply my linear transformation to the sum of these two vectors, linear transformations are going to do what linear transformations do and send a sum to a sum. So the 330 component is getting sent to 303. But this difference between my two vectors in the domain, that difference is getting sent to 0. And so t of v2 is going to be 303 plus t of this vector, which is the 0 vector. This is why the difference between these two vectors gets lost in this linear transformation, because the difference is an element of the kernel, and the kernel is that stuff which is getting sent to 0. So in other words, this failure for this linear transformation to be injective was only possible because the difference between these two different vectors was an element of the kernel. And so if we were to look at all of the vectors that have the same image of 303, they would all lie along this subspace through v1 and v2, which is parallel to the kernel of t. So the only way to ensure that this doesn't happen, the only way to make sure that a function is an injective linear transformation, is to make sure that we can't have a situation, like we had here, where my equation, a with a b on the right-hand side, which in this case was 303, we don't want it to have infinitely many solutions. That's where we got this erasure of difference that caused this to fail to be an injective linear transformation. But this equation has infinitely many solutions if and only if that same equation with the 0 vector on the right-hand side has infinitely many solutions, right? Because how many solutions a linear system has is really controlled by the number of free variables, and the number of free variables is just the number of non-pivot columns that I have over here on the left-hand side of my augmented matrix. It doesn't matter what I put over here on the right-hand side. So if I put the 0 vector on the right-hand side, now we can see this as having something to do with the kernel. And so if I want my linear transformation to be injective, I need to make sure that the homogeneous equation does not have infinitely many solutions. And the only way for the homogeneous equation not to have infinitely many solutions is for it to have exactly one solution. Namely, for every column of A to be a pivot column, and that happens if and only if the kernel of my linear transformation consists only of the 0 vector. When the homogeneous equation has only one solution, in other words, when my linear transformation only sends a single point in my domain to the 0 vector in the codomain, that point which it sends to the 0 vector in the codomain must have been the 0 vector from the domain. After all, the 0 vector in the domain always gets sent to the 0 vector in the codomain. But for an injective linear transformation, it is only the 0 vector from the domain which is getting sent to the 0 vector in the codomain. So a linear transformation is injective if and only if its kernel consists only of the 0 vector. That's going to make the homogeneous equation, and therefore every other consistent equation for that linear transformation, have only one solution. And that's going to make sure that my linear transformation does not erase differences. As we were saying before, this is only possible if all of my variables in the reduced row echelon form are bound variables. As soon as I have a free variable in this system, I'm going to have a non-zero vector in my kernel, because I can choose a non-zero value for that free variable and give me a non-zero vector, which is a solution to the homogeneous equation. So an injective linear transformation can have no non-pivot columns. In other words, every single column of the reduced row echelon form of A needs to have a pivot. That's how we can recognize a linear transformation as being an injective linear transformation. Now, let's reset ourselves and imagine the situation where I want to solve the linear equation tx equals b, and I'm going to choose the vector 0, 0, 2 as my b. So this is going to be my right-hand side. So I'm picking a vector here in my codomain, and I'm asking, is there some vector x in the domain for which t of x is equal to 0, 0, 2? In other words, if I try to solve this augmented matrix equation, am I going to find a solution? Well, the reduced row echelon form does its work. We take a look at that last row, alarm bells go off. This last row is the equation 0 equals 1, which is a contradiction. Therefore, this particular b, right-hand side, does not give us a consistent equation. There is no x vector in the domain for which t of x is equal to this b, 0, 0, 2. So it's possible, for at least one choice of b, for t of x equals b to be an inconsistent equation. So from our language of sets and functions, we would say that t is not an onto function, because there's something in the codomain which is not realized as the image of something from the domain. In particular, in this example, we've shown 0, 0, 2 is such a thing. So t is not an onto function. And for linear transformations, we doll that up with the word surjective. We say t is not a surjective linear transformation. So turning that definition on its head, we do have a surjective linear transformation if this can never happen. If t of x equals b is always a consistent equation no matter which b that we select. It means that the entirety of the codomain is covered by the outputs of t. So when I apply t to all of the vectors in my domain, it spits out all of the vectors in my codomain, so that t of x equals b always has at least one solution. So this has everything to do with the consistency of equations that are built from my linear transformation. T is a surjective linear transformation if the augmented matrix equation with the standard matrix and a b on the right-hand side is always consistent no matter what b that I place here. I can write whatever 3 entries I want over here, and when I do the reduced row echelon form, I never get a contradiction. That would be what would happen if we had a surjective linear transformation. So how can we test for surjectivity? Let's again ask the question, how was it possible for surjectivity to fail in this example? How did this all happen? Well, it happened because, remember, all of the outputs from my linear transformation form a subspace of the codomain called the image of t. And we saw in our previous video, the image of this linear transformation was a 2-dimensional subspace of the 3-dimensional codomain. It was the plane that had equation minus x minus y plus z equals 0, or which had a basis minus 1, 1, 0, and 2 minus 1, 1. So it's this 2-dimensional plane, the image of t, sitting inside the 3-dimensional codomain. And that presented a problem for solving tx equals b for this particular b, because this b is not one of the outputs of my linear transformation. This b does not belong to the image of t. When we have this equation for it, we can check that minus the x-coordinate minus the y-coordinate plus the z-coordinate is not in fact equal to 0. So this b did not belong to the image of t. That's why this tx equals b was an inconsistent system. So in order to rule out that possibility and have a surjective linear transformation, we need to make sure that it is not possible for anyone to choose a right-hand side vector, a b, which is outside of the image of my transformation. So the image of my transformation has to cover the entirety of the codomain. So the image and the codomain have to be the same thing if t is a surjective linear transformation. Remembering that the image of a linear transformation is spanned by the columns of its standard matrix, this also tells me that the columns of my standard matrix, if my transformation is surjective, need to be a spanning set for the entirety of the codomain. Because if my columns span the entire codomain, it will not be possible for me to pick a b vector which is not equal to a linear combination of the columns of my standard matrix. And therefore, we must have a consistent system. Well, what is a better way to rule this out? From a computational perspective, if I want to prevent this inconsistency from ever happening, no matter what right-hand side you give me, I can rule out the possibility of getting a contradiction down here, only if I can guarantee that none of the rows of my reduced row echelon form are going to disappear. So in order to prevent inconsistency, we need to prevent any non-pivot rows from the reduced row echelon form of my standard matrix. And so a linear transformation will be surjective if we do not have any non-pivot rows. In other words, if all of the rows of my reduced row echelon form of my standard matrix are pivot rows. So now that we're looking at all of these consequences, injective and surjective look computationally very similar. An injective linear transformation is one in which all of the columns of the reduced row echelon form of the standard matrix have pivots. Surjective means that all of the rows have pivots. And the best possible situation, the one that we like the most in linear algebra, is one in which both of those things happen simultaneously. We call those linear transformations bijective, if they are both injective and surjective at the same time. So all columns would have pivots and all rows would also have pivots. So if I had a bijective linear transformation, we know that any equation built from that transformation will always be consistent no matter what right-hand side that we put because of the surjectivity. And also that the solution set of this system would have only one vector in it. There would be a unique solution for t of x equals b because of the injectivity. So the reason we like bijective linear transformations is we can always solve t of x equals b, no matter what right-hand side, and get exactly one answer, x. It maps exactly one vector in the domain to exactly one vector in the codomain in all cases. So injective and surjective gives us bijective, which is our favorite.